Do you know why the collector region is always larger than the base and emitter? And what is meant by thermal runaway? If you guys need to know these topics, so please continue watching this lecture. So I will be letting you these both are how we can explain it in a simple terms. So last class we have detailed discussed about how the things like what will be the effect of the like the doping effect and as well as the other things is like the heavily doped substance is emitter and moderately doped is the base and collector is mostly lightly doped and the size of the collector will be larger and the size of the base will be very thin. So taking both into advantage or taking both into account, so let's see what will happen in the thing. So we know that whenever temperature increases, the ICBO, so which is the reverse saturation current that we have discussed already, right? So that will increase because we clearly discussed this is some temperature dependent parameter and that is considered in the reverse saturation and then some negligible increase in temperature that will happen here. So if the ICBO increases, then what will happen? IC also increases because IC is the ICBO is directly added to IC. So if this is happening, then what will happen? If the temperature is keep on increasing, then the ICBO will increases and IC will increases. If the IC increases, then what happen? The temperature or the temperature of the diode or temperature of that particular junction will also increases. So if this is happening, then as we know, as the IC increases, temperature will increase. So if temperature increases, IC will increase, IC increase. So this is a loop. So you guys able to get it right. So this is a circular loop. So this is depend on this one, this is depend on this one. So this will what will happen is that this term which is called the loop which is called as a thermal runaway. I hope you guys getting right. So the effort, the temperature effort causing IC increases, the effort itself causing that cause. This is the cause, this is effect. So the effort is again causing the cause to increase. So this is on loop. So we can't stop it. So in order to avoid this only, we are making the collector region to be larger. So if we take the collector region, larger, if we take collector large in area, then power per unit area will be reduced. Power per unit area will be reduced. Power per unit area. Okay, because large area, right? So power dissipation will be more. So we can reduce some kind of things. And we can prevent the transistor. We can prevent the transistor to thermal runaway. So we can prevent the transistor from thermal runaway. So thermal runaway is a critical worst process that will make the transistor die. So we need to avoid that. So in order doing that, we usually have the larger area of the collector. So this is thermal runaway. Okay. So I hope this you guys getting right. So this is one of the critical point that we have to discuss whenever we are discussing the BJT, because this term is a very crucial, right? So whenever there is any kind of effect with the thermal runaway, then the transistor will be dying. Okay. So as we know, every time while we are discussing any kind of device related thing, so we for sure discuss about energy bands. So let's today we discuss about active region. So active region is the one thing we discuss, that is forward and reverse bias. So active mode energy band diagram. Okay, so let me draw how the energy band diagram which will normally look and how that will change when we change it. So all the EC level will be at the same level. So this is we know very well. So I'm drawing entirely. So all the EC will be at the same level. All the EV will be at the same level. What the thing will change is the donor and acceptor atoms Fermi level only will change. Okay, so let me erase it. So this is for the one type semiconductor. This is for next time semiconductor. So three region, right? So three things I have drawn separately. Okay, so then this is P type. So let me take this as a PNP transistor. So which is PNP. So the Fermi level of the P which will lie here. So which is 0. This is heavily doped. So this will have some quite larger concentration. So that is drawn much below. So even I can draw it much below. Okay. So this is N type, right? So Fermi level will be quite top. So you see the distance between this and this is larger because you know this is heavily doped. So heavily doped, the concentration carrier will be at the top or will be that. So this is NPN. So this only this only plus. So this only plus. So this is not. So this one we need to draw it little upper. Okay. So I hope you guys are able to understand, right? So why this distance? This is closer and this is away from the EC and EV. Okay. So this is very important thing. So please don't blindly remember if they draw anything. So we have the definition for everything. So this is the Fermi level. So when we connected these, both the junctions are connected, how the things will change is that. So let me draw. We already know this, the all the Fermi level will be combining. So this one, the netted difference here, right? So this one, this one. So this distance will be adjusted. So that is what the thing. So that is what the nature. So when we combine the junction, the Fermi levels will be at the same level, because now this is going to act as a single device. So means, first let me draw a Fermi level. So this is the Fermi level. All the EF will be same, right? So all the EF will be same. So if you see, what we can do is that we can fix the middle n. So now this gone up. So this means it will go up. Okay. So let me draw a easy here. So this is the easy. So let me draw it. And this one will also be adjusted. It will go up. But this has to go much larger distance. This is quite smaller. So I have drawn little below that. Okay. So then this is adjust here. So this will be at the same level. So that I am drawing as it is. Okay, so I have drawn it. So below also same thing, the same replica. So it has gone up, so it will also go up. So let me draw it quite closer. Here you can see this distance and this distance need to be quite same. So then this will also go down. So I go down, gone down, and this will also be, but the distance will be quite larger than this one. Okay. So this is what the thing that we will be getting. Okay. So thing is that, so this is JE. So this is JE. This is JC, collector junction, emitter junction. So these all are joined. So we have to now merge these things. So if we have to keep the thing is that, so this is normally it will how it will occurrence. So this is normal. So if you have to convert this into active region, then what will happen is that we need to take, as this is an active region, so this the width will be, so let me draw the normal thing first, so that you guys can quite able to understand. So let me copy this to another page. Okay, so this is normal. So let me draw. This is normal energy level. This is not for active level. So please don't confuse this one. Okay, this is normal energy level. So let me combine the states. So this will be joined to this one. This will be joined like this. Okay. So now what will be the general thing is that this is EF, this is EC, and this is EV. Okay. So this is normal. So we haven't provided any forward bias or reverse bias there. So this is a general thing of discussion. So this is the width of difference that we need to come across. So the electron or a hole need to jump from this to this. So this kind of external potential that we need to apply. So this will be QVOEB. So this kind of VOEB. So that is the potential that we need to give. So in order to make that jump from this one. So here there is some potential, right? So this one, this coiled differential will be QVOCB. So this is the backend second port 2 applied potential. This is port 1 applied potential. So based on the things will go. So here more number of electrons should be present. So that is an electron. So more number of electrons which need to jump, or which need to jump here and which need to jump here. So that is what the criteria that we need to match here. So this is PNP transistor. Okay. So this is normal energy level without anything. So let's see when we are giving the potential. So this is at equilibrium. Okay. So this is at equilibrium. So I net will be equal to 0 because there is no external things that is causing, right? So that is, so this is the active region that we are going to discuss now. So this is the active mode. So active mode means the JE which is forward bias and JC which is reverse bias. Okay. So we discussed the criteria, right? That one. So if you do it, the what will happen is that this width will be reduced because that we are applying some kind of potential here. Okay, I think we can't do it. So let me draw it from scratch. Okay, so the EF, so based upon the thing means the forward bias and reverse bias will come into picture. So let me first draw EC here. So this is the EC. this is EF, and this is EV. Okay, so EV will be quite closer because we know that is heavily doped. So next, the actual this is a PNP transistor. So let me draw the N-type region. So because of this forward potential, then the difference between this barrier will be quite lower. So I am drawing it the P-type here. Sorry, N-type's EC here. Okay, so N-type EC, the next one also lie here. Okay. So for me, let me skip the energy level for now. So in the P-type, so this is completely reverse bias, right? So the potential will be moving much upper. So here I am drawing this here. Okay, so now let me connect the lines so that you guys can understand it. So this is the difference in things. Okay, now you can see this is forward bias. So this junction, this is N plus, sorry, P plus. So this is forward bias, right? So means you can clearly see the difference in potential between those things is very low. So the electrons which are present here can easily come here, and holes which are present here, right? So below the Fermi level, holes will be there. So this is the EF. So now what will happen? These holes can easily move to here. So electrons will move, jump, holes will easily move. So the holes will be formed here. Holes will come here. So I am writing as virtually. So then these holes need to jump here. So that is what the current we produce. So that is the thing here. Okay, so that is what the thing. So here the potential difference that what we need to give here, or what we will be giving, this is the, we will be providing reverse bias potential, right? So in order to, so the thing definitions we have already discussed. So this will be Q VOCB plus modulus of VBC. So this is the barrier potential that we will be getting because of reverse bias. This will be get added here. So think here, because of the forward potential, the difference in width will be here Q of VOEB. So VOEB is the natural electric field or voltage difference. So when we apply the forward potential, that will be subtracted by VEB, right? In the previous class, previous thing we have seen, this is a VO. So VO is the normal natural barrier without any external supply. So here if we provide a forward bias, that is a considered subtraction. So here it is reverse bias, so that is taken into plus. So I hope this is understood. So from here you can clearly see, so this is reverse bias and this is forward bias, and how the current will move, and those things we have already discussed, right? So here there will be a movement, that is INE. So if you guys face difficulty to find the understanding of electron movement, charge carrier movement here, then I prefer you guys to watch my first lecture on the BJT. So there we have discussed in the device level understanding, so that will be quite easier for you. Okay, so this is how the current will go. So now you guys can able to understand how the energy level and the band things will vary when we have the things. So this is what the general device level understanding. So I hope you guys can able to understand how the electrons are moving in the both the device level and as well as in the energy band level. So I'm stopping here. So I'm leaving this to you. So if you guys have any doubt, please post in the comment section. Please like, share and subscribe the channel so that you guys will be get notified on all of my lectures. So stay tuned guys. So next class we will be seeing one of the important application, that is early effect. So that is, we already seen in a PN junction diode discussion, we have seen some resistance and capacitance effects, right? So similarly in BJT we will have some resistance and capacity effect. So that thing, because of that, some early effect will come into picture. I will be explaining you that in a very good manner. So please stay tuned or watch that. Thank you guys.